Infuriating? All right, we're gonna move a little bit more quickly here if we can. Not at the risk of not understanding though. We got a spherical balloon that's being inflated at a constant rate of 5 cubic inches per minute. So this is kind of how we started this section. When the radius is 4, how fast is the surface area changing? That one makes it a little bit more interesting. Okay, so drawing a picture. Let's go ahead and use a red balloon. Just one though, not 99. It's too many to draw. And we have a radius right there. It's being inflated. So there you go. Air is going in at 5 cubic inches per minute. And that is going to be a direct rate of change of what quantity? Volume. Yeah, if you're not sure, just look at the units. Cubic inches is a measure of volume per minute. That's a unit of time. So I'm going to go ahead and call the volume V, and that then would be, in Leibniz notation, dV dt. And because we're inflating it, is it a positive or negative rate? Positive. Okay, so there's dV dt. Got it. The radius is really the only one we need when the radius is 4. So there's our snapshot moment. When the radius is 4, how fast is the surface area changing? So the surface area I'm going to call A, and so we're looking for dA dt. There's our target. Now, I need to be able to relate somehow the quantities, volume to area. And I can relate them directly, or I can relate them somehow through a third party. All right? Now, here's what I do know. I know that the volume of a sphere, and you should too after today, it's 4/3 pi r cubed. That's one you want to remember. And I know that the surface area of a sphere is actually its derivative with respect to r. It's 4 pi r squared. That's another one you need to know. Now, you have the option, like I said, of either relating the area directly to the volume or going through some third-party variable like r. What would you prefer to do? Well, let's see. I have two equations. I ultimately need to relate their rates to each other. And since I have both of the equations, let's go ahead and take the derivative of both of them so I can introduce a dV dt and a dA dt. So this one would be when I take the derivative of both sides with respect to t, I get dV dt equals, and as you might expect, we get 4 pi r squared, the surface area equation, times dr dt. Let me redo that pi, doesn't look so good. And up there, if I take the derivative of both sides with respect to t on the area formula, I get dA dt equals 8 pi r times dr dt. Now this is why I need both of them. dA dt is my target. That's what I'm after ultimately for this problem. But I was given a rate of change of volume. Okay? Now notice what I need to evaluate the dA dt is I need to know the radius at the given moment, which I do. That's my snapshot moment of 4. And I need dr dt. So it's really dr dt that's the missing link. So you could do one of two things. You can actually plug in your 5 to this dV dt equation right now and get what dr dt is at the moment, or you can solve it with variables with dV dt still in there and then substitute it into your dA dt problem. And then it becomes in terms of dV dt. I don't care which one we do. Which one would you like to do? Work with numbers or work with variables? Probably numbers. Okay, so let's do that. So when r equals 4, here we go. I'm going to plug it into this equation right here. dV dt, which was given to be 5, is equal to 4 pi r squared, which is 4 squared, times dr dt. I don't know what that is. So now I can solve for dr dt. That means dr dt is equal to, let's see, it's going to be 5 divided by 4 squared times 4. That's 16 times 4. That's 64 pi. What a wonderful number. Okay, so that's what dr dt is at the moment. Now I can use that right here. Okay? So dA dt at the moment equals 8 pi times r, which still at that snapshot moment is 4, times 5 over 64 pi. If you would have plugged in with variables using dVdt, you probably could have simplified some of your pi's and stuff like that. But we're working with numbers, and so there's dA dt. And if I simplify that, good things should happen now. Notice I get a 32 pi, and then divided by a 64 pi, that gives you a 1/2 times 5 is 5/2. So the number turns out to be pretty nice. And of course, once you get 5/2, you didn't have to track your units all the way through. You can just look units of area over units of time. We're talking about inches squared per minute. All right, it might be, you want to look at the other way we could have done it? It looks like it simplifies quite a bit. The other way we could have done it is straight from down here. You could have solved for dr dt, and it would have been 1 over 4 pi r squared times dv dt. And then you can plug that in up here to get this equation. And we're running out of room. dA dt would equal 8 pi r, and then times 1 over 4 pi r squared would be 4 pi r squared in the denominator times dr dt. And of course, if you simplify that, now I can zoom in. dA dt would equal, let's see, your pi's divide out, and you get one of your r's divide out, so you're left with 2 over r times dr dt. Oh, I'm sorry, times dv dt. My bad. That would be dv dt. I'm getting lost now. dv dt. There we go. So again, any way you can get there. That's the rate equation then that relates the rate of change of the surface area directly to the volume. And if you had to do multiple calculations, it might be better to work symbolically with letters, simplify, and then plug in repeatedly. But we were just doing one calculation. So in this case, we kind of had to wend our way from where we wanted to, or where we started to where we wanted to get, and we had to go through this third-party quantity. So you'll always have enough information given to you to ultimately answer the question. You might just have to go in search of your information first, okay? So pretty good little question right there. Any comments on that one or any other questions y'all have? All right. Example 7, 2 cars are riding, I guess, traveling, riding, I don't know, cars ride, or driving. Cars don't drive themselves. Well, now they do.
Just reminder students, if you were absent yesterday, please remember to come to the back office to pick up your report card sometime today. Also, another reminder, NHS candidates are reminded that all candidate information, including the application, references, and documentation of service hours, is due on or before Friday, January 8th, 2016. If you have any questions, see Ms. Gray in room 103.
Teachers, will you please turn your TVs to channel 4 for the morning announcements, or you can view them on your iPads at mhstv.com.
Okay, so we got 2 roads. There's an intersection, okay? This is the last one we'll do for today, and this one's actually pretty easy. Car A at the moment is 3 miles south of the intersection. So the intersection is right here where they cross, and I just drew a little dot here and called it capital A. I'm going to call the distance from the intersection little a, and at the moment it's 3. And it's traveling north, okay? So it's going up, it's moving up, and it's moving up at 40 miles per hour, so that's its rate of change. So dA dt is going to be some type of 40. Is it going to be positive 40 or negative 40? Negative, and this is cool. Even though it's going up, right, normally up is positive, we're talking about this being the distance, and it's closing in on the intersection. So the distance between it and the intersection is decreasing, so it's negative. Excellent. Car B is east of the intersection, traveling east, okay? So let's use a different color here. East of the intersection, so it's going to be over here, and it's only 2 miles. So I'll go ahead and call that little b. And at the same moment, the snapshot moment b is 2, but it's continuing on this way. So its rate of change, and how fast is it going? It says it's going 50. So dB dt is positive or negative 50? Positive. It's moving away from the intersection. So the intersection is our point of reference here. And then it says, at that moment, how fast is the distance between the two cars changing? All right, so I'm going to go ahead and draw that with this brown line right here. And what do you want to call that? It's changing, so we need to label it as a variable. I'm going to go with C. You might want to stay away from D if you can, because when we use Leibniz notation, of course, we have D. Unless you want to call it big D, right? We need a new big D because this year Big D, Dallas didn't do so well, didn't make playoffs again, but anyway, that's another story. So, we're looking for DC dt, the way I labeled it. What's the equation that relates them? Pythagorean theorem, good. So, this becomes a squared plus b squared equals c squared. And they're all changing, right? So, it's not like the problem where we had the ladder or like the quiz where it was a fixed value. They're all changing. So now we'll take the derivative with respect to t, and we get 2a dA dt plus 2b dB dt. It's always funny. 2c dC dt. And of course, it's always your prerogative to divide out the 2's all the way across to make the problem a little bit maybe easier. But you do have 6 unknowns there. And if we're trying to find dC dt, that's the only one that we're allowed not to know. So we need to know the other 5. So at the moment, I think we do know A and dA dt, and we know B and dB dt. Schroeder, we're just missing which one? We're trying to find dC dt, good. So we are missing it. Yeah, we are missing it. True. We're missing C. So let's go ahead and find it by the Pythagorean theorem. 2 squared plus 3 squared equals C squared. Is this going to be a nice Pythagorean triple? C is going to equal the square root of 4 plus 9, which is 13. Okay, so we'll take it. So now we plug in. So we say when, and we just reference the moment in time by referencing either one of them. How about when A is 3? When A is 3, we get 3 times dA dt, which is its rate, which is negative 40. And then plus B, which is currently 2, times dB dt, which is 50. And that equals C, square root of 13, times dC dt. Now notice, because over here on the left, you're actually adding, or in this case, subtracting 2 numbers. If you get your sign wrong, SIGN, on your rates of change, you're not just going to get like the opposite of the right answer. You're going to get a completely different number because you're subtracting or adding instead of the other one. So let's see, what do we get on the left? We get negative 120 plus 100, which is negative 20 divided by the square root of 13 equals dC dt, and that would be in miles per hour. So you can write it like that, mph. So the distance between them is actually decreasing by whatever that amount is, miles per hour. So another right triangle problem, but in this case, all 3 sides are changing. I have seen problems like that where the roads intersect at a weird angle, like over there at 1863 and 46, right? In which case, you can't use the Pythagorean theorem. You have to use the super-duper Pythagorean theorem, known as the law of cosines. But I haven't seen one like that on AP exam. But, you know, they do exist. Law of cosines. Remember, the law of cosines would just be this. The only difference would be if we have c squared isolated, the law of cosines, a.k.a. the super P theorem, it would be c squared equals a squared plus b squared, right? Then you got this little adjustment, minus 2ab cosine of theta, where theta is the angle at C, okay? And of course, if it's 90 degrees, what's cosine of 90 degrees? 0. This whole piece comes off, so it kind of modifies it for any triangle. Okay, that's a good place to stop. Tomorrow we should finish. I'm gonna push tomorrow. We won't have a quiz. You know, I might skip example 8 and just go straight to the fruity flavored raspa problem. Yeah, that's the Niño Corpi problem. We got raspas. and then we'll work one from an AP exam, and then we'll talk about a young boy running at night. Ooh, what a way to end. Okay, so be working on that Relator 8 worksheet. It'll be due on Monday. We'll probably have another short quiz on Monday, not one of these awesome ones like today.